Hello friends, let us solve some examples of functions where the examples are of 1 1 on 2, that is bisective, and inverse. So let us take few examples. So let us have a function f from minus 1 1 to minus 1 1. Fx is equal to x modulus x. So this function is of which kind? So 1 1 and on 2, then many 1 and on 2, then many 1 and not on 2, that means not neither 1 1 nor on 2. And the fourth option is 1 1 and on 2. This is bisective also. Many 1 means not 1 1. Okay, the function is fx is equal to x modulus x. Even you may also be given r to r also. Okay, so this is nothing but x square if x is greater than or equal to 0 minus x square if x is less than 0, because we know that modulus x is equal to x when x greater than or equal to 0 minus x when x less than 0. Even if we draw the graph of this function, then it look like this. From 0 to infinity, here you are given minus 1 to 1, so you may even consider 0 to 1 also. The graph is like this. Okay, and it's a parabolic graph. Okay, and in minus 1 to like this. And so you can see that even from graph also, if you draw the horizontal line in the graph, if it cuts only at one point, then the function is 1 1. Okay, and here you can see that it covers all the points between minus 1 to 1. That means it is on 2 also. Okay, so here f is 1 1 and on 2. Okay, so the answer is 1 1 and on 2. Okay, here two options are same, 1 1 and on 2, many 1 and on 2, many 1 and not on 2. So let us write like this, 1 1 and not on 2. Okay, let us take next example. If f from r to r fx is equal to 2x minus 3, then f inverse x is blank. The options are f inverse f is f itself, then x plus 3 by 2, then f inverse does not exist, and fourth is 3x minus 2. So here we can see that this is a linear function. So it represents a line, and it's always a 1 1 on 2. It's always 1 1 on 2, and therefore f inverse definitely exists. Now for f inverse x we do like this. F inverse we do like this, say fx is equal to y. So 2x minus 3 is equal to y, and therefore x is equal to y plus 3 by 2. This is the way you can easily find out the f inverse, and even on 2 also. Okay, so f inverse y is y plus 3 by 2, and therefore f inverse x is x plus 3 by 2. So the answer is here B. Okay, next let us see f from minus pi by 2 of close interval minus pi by 2 to minus 1 1 is a bijection if fx is blank. That means which function is 1 1 and 1 2. Here the options are modulus x, sin x, x square, and cosine x. Okay, so see, we know that modulus x is not 1 1 in any interval having minus negative and positive value. So that modulus x is not 1 1, because modulus x, you know, its graph is like this. So when you draw the horizontal line, it cuts at 2 points, so it's not 1 1. Similarly, say x square is also not 1 1 in minus pi by 2 to pi by 2. Okay, that we easily in fact have the idea here that say suppose f of minus pi by 4 is same as f of pi by 4. Okay, so at two different point you are having the same value. Similarly, for cosine x also, the value of the function cosine f of say even minus pi by 2, both are included, and f of pi by 2 are same, so that is also not 1 1. We know when we define the sine inverse function. Okay, so sine function is in minus pi by 2 to pi by 2, it is 1 1 and on 2. So the function minus pi by 2 to pi by 2 sine, and its graph is also easy to draw. Sine minus pi by 2 is minus 1, then sine 0 is 0, and like this. So the graph of sine function in minus pi by 2 to pi by 2 like this. And so here we can easily see that if you draw any horizontal line, it cut at only one point, and the region cover here all the points between minus 1 and 1. So it is 1 1 as well as on 2. So sine function is 1 1 and on 2, or you can say bijection. So the answer is sin x. Okay, let us take one more. F from R to R, fx equal to x square plus 2x plus 3. So is blank. The options are a bijection, 1 1 but not on 2, 1 1 but not on 2, then on 2 but not 1 1, and D many 1 and not on 2. Many 1 and not on 2. So now let us see, this is not difficult. Fx is equal to x square plus 2x plus 3. Can we write this as fx is equal to x plus 1 square and plus 2. Okay. Now if we take x is equal to, say, suppose minus 3, then f of minus 3, so minus 3 plus 1, minus 2, its square is 4, plus 2, so that is 6. So here minus 3 plus 1 square, so minus 2 square. So you can have one another value of x where we are having 2. So even if we can take x to be equal to 1 now, so that is also 6. That means f of minus 3 equal to f of 1, and you know minus 3 is not equal to 1. So what does it mean? F is not 1 1. Even f is not on 2 also, because fx is equal to x plus 1 square plus 2. So that is greater than or equal to 2. That means the range of f is not R. Range of f definitely subset of 2 to infinity. So range of f is not R. So therefore f is not on 2. That means f is neither 1 1 nor on 2. So the option is D. So therefore f is many 1 and on 2. So that is the option D. Take one more. So these are the kind of examples that you are having for 1 1 and on 2. Let us take this one. If f from R minus 1 to R such that fx is equal to x over x plus 1. So is that function is 1 1 and on 2, then 1 1 and not on 2, then third not 1 1 and not on 2. That means neither 1 1 nor on 2, and on 2 but not 1 1. Okay. Now fx is x over x plus 1. So we can easily see that it's 1 1. You can prove it also. Fx1 equal to fx2 will imply x1. So this is also a method to prove to be 1 1, that if fx1 equal to fx2 implies x1 equal to x2, then f is 1 1. So fx1 equal to fx2 implies x1 over x1 plus 1 equal to x2 over x2 plus 1. And if you take the cross multiplication, x1 x2 plus x1 equal to x1 x2 plus x2, and so this would imply x1 equal to x2, and so f is 1 1. So f is 1 1. Okay. Now what about fx? What about this on 2? Let us try to see. Even if we observe something, then also we can see that, but let us see. See, for onto we take y is in R. So fx is equal to y implies x over x plus 1 equal to y, and this would imply x equal to xy plus y, and this is x minus xy equal to y, or you can have x equal to y over 1 minus y. Okay, so from these we can easily see that the element 1 do not have image. See, that means 1 is not in the range, because if 1 in the range, then for some x fx equal to 1, that means x over x plus 1 equal to 1, that means x equal to x plus 1, and that means 0 equal to 1, so which is not possible. That means 1 is not in the range, and therefore f is not onto, because range of f is not R. Range of f is not R, and therefore f is not onto. So f is 1 1 but not onto. So 1 1 and not onto. So option B is there. Okay, let us take one more. F from R to R, fx is equal to x minus integral part x, then f inverse x is blank. So the options are does not exist, then x, then integral part x, and x minus integral part x, that means f itself. But see, this is very easy to check, that if I take say f of 1, then this is 1 minus integral part 1, and so 0. F of 2, 2 minus integral part 2, so we know that is 2 minus 2, so 0. That means f is not 1 1. Once f is not 1 1, there is no question of inverse exist. So f inverse does not exist, because for existence of inverse f should be 1 1 as well as onto. So this is the option. Okay. Let us take this one. Similar example, f from R to Z, fx equal to integral part x. I am not writing the options, but you can easily see here f is not 1 1. F is not 1 1, because it's easy to see f of 1.2 integral part 1.2, it is 1. F of 1.4 integral part 1.4, so it is 1. So therefore f is not 1 1, because f of 1.2 equal to f of 1.4, but 1.2 is not equal to 1.4. Now you know what is the range of the integral part function. All integer values are there, so that is z, and here already you are having the codomain as z. If it is written as R, then that is not onto, but here it is written z codomain, so you can say that f is onto. So you should take care what is the codomain here we are given. Okay, next. If f from z to z f of n equal to n plus 2 when n even to n plus 1 when n odd. So the question is, then f is blank. That means 1 1 on 2, neither 1 1 nor on 2. So that kind of options are there. So we need to check whether it is 1 1 or 2 or not. So here when you are having z to z is there, so we should try some options, some values of the function, like f of say minus 2. So that is even, n is even, so minus 2 plus 2, and so the value is 0. F of say minus 1, so minus 1 is odd here, so that value is 2 into minus 1 plus 1, so that is minus 1. You can have f of 0, 0 is even, so 2. Okay, then f of 1, so 1 is odd, so 2 into 1 plus 1, so 3, and so on. Okay, now here you can see that when n is even, n plus 2 is also even, and when n is odd, you can take n is odd, then 2n plus 1 is odd. Okay, if it is needed, you can have that kind of things, but right now it is not required. Now here you can see that the value of the integers are different, 0, minus 1, 2, 3. No value will remain same, and it is so because yes, here it is useful because see, this n is even, then n plus 2 is also even. N is odd, then 2n plus 1 is also odd. So even and odd never be equal, first of all. So these two will never be equal. Okay, and so you can definitely say that f is 1 1. F is definitely 1 1. Different values are having different images. What about on 2? And that part we can have here 1. Say 1 is not there in any image. You can see that 1 is not in the range, because there is no, here it is 0, minus 1, 2, 3. So 1 is not looking in the range, minus 3 suppose, then so 1 is not there. Okay, so that means f is not on 2. F is not on 2. So f is 1 1 but not on 2. Next, let us see f from z to z fn equal to n plus 1 when n even, n minus 3 when n odd. So here also we need to check for the 1 1 and on 2. So say here also we can take some values like f of minus 2, n is even, minus 2 plus 1, minus 1. F of minus 1, n is odd, minus 1 minus 3, minus 4. Say f of 0, 0 is even, so 0 plus 1, so it is 1, and so on. F of 1, so 1 minus 3 minus 2. You can have f of 2, so that is 3, and so on. Now just by these few values, you can have the idea that the values are not, images are not repeated. Okay, so looking to this, we can definitely say that f is 1 1. See, to solve the MCQ, we don't need to prove or waste some time. we need to do very quickly. Okay, so f is 1 1 is sure, and we can have f is on 2, so it's looking like 0. 0 is not there in any image. Okay, 3, then it is 0. Yes, when you take f to be 3, then it is 0. 0. Okay, 1 minus 1 minus 2. 2, does 2 is in any image? So what getting 2 as the image, see when n is even, n plus 1, so this n plus 1 would be odd, because n even, just add 1, so that will be odd. When n odd, and if you just subtract 3 from that, so if you subtract 1 from that, it will be even. 2 from that, it will be odd. 3 from that, it will be even. Okay, so this will be even number. Okay, how this is helpful to check some of the things. And now, so we are not having like 1 minus 1 2 2 suppose. So 2 does 2 in the range? That is the question we are asking. Does 2 in the range? If it is there, it will be here itself, because 2 is even and here itself. Okay, so it's there in the range, because if I take 5 is odd, so 5 minus 3, so it is 2, so 2 is in the range. You understand? So we are having on 2, then then 2, then 3 is there. Does minus 3 is there? So if minus 3 is there, it would be here itself, because this part is odd. So if it is minus 3 is in the range, then you are having n plus 1 should be minus 3. So n should be equal to minus 4. So if I take minus 4, that image is minus 3. So it seems that the onto is also there. Okay, so just by trial and error, you just check and very quickly you can have the idea that it is 1 1 as well as onto also. Okay, that means it is both 1 1 as well as onto. So does minus 2 is in the image? Minus 2 is even, minus 2, minus 3, so if 1 is taking, then minus 2 is in the image, like this. Okay, fine. Let us take one more example. F from Z to Z, f of n equal to n when n even, and to n plus 3 when n odd. Okay, so here also we can see like f of minus 2, so here even, so it is minus 2. So when n is even, the value is n itself, and when n is odd, say f of minus 1, so 2 into minus 1 plus 3, so it is 1. Like f of 0, then it is 0, but f of 1, then it is 2 into 1 plus 3, so 5, and so on. Okay. So here we can see that the different elements have different images, and it's easy to see that f is 1 1. Okay. And another way is also you can have, because when n is even, n is, so this part is even, and when n is odd, this part is 2n plus 3, so that is odd. Okay. Okay. Now is there anything where the onto breaks? That means some of the elements may not have the image, like 2 suppose. So 2 n is even, okay, that is there. Then some elements may not have the image, like -2, then 1, then 0, then 5, then 2, say 3. Does 3 is in image? So let us try to see. Does 3 belongs to the range? Now 3 is odd, so if it is in the range, it will be here only. It will never be here. So it will be here in 3. So it should be 2n plus 3 should be equal to 3. So 2n equal to 0, n equal to 0, but n0 is not odd, it is even. That means there is no odd number you are getting where 2n plus 3 is 3. That means 3 is not in the range. F is not on 2. Okay, it is 1 1, but not on 2. Okay. Next question. If f defined like this, say n cross n to n cross n, f of mn equal to nm, then f is blank. So now this is not difficult. Here the easy you can check for the 1 1. Easily you can check for the 1 1. So f of m1 n1 equal to f of m2 n2. So this would imply image of f of mn is nm, reverse thing. So this is n1 m1 equal to n2 m2, but this would equal to n1 equal to n2, m1 equal to m2. This you can take the equality. Okay, and so this you can say that m1 n1, so m1 is m2, so that is m2, and n1 is n2, so you can say here n2. So m1 n1 equal to m2 n2, and that implies f is 1 1. Now what about onto? Onto is also there. So you can have like, let m comma n belongs to n cross n. Then can you say n comma m belongs to n cross n? Answer is yes. And if I take f of nm, then by the definition of that function it is mn. So whatever the element we have taken here, we get that element as the image of some element. That means f is onto. F is onto, and therefore f is 1 1 and onto. See, if someone 1 1 and onto, that means f is bisective. Someone may also ask the inverse. Inverse F inverse is what? So F inverse like this Mn can be asked, but that will be seen from here. Okay, so F inverse Mn is, we are having Nm. Okay, and so F inverse Mn is a Nm, that means that is nothing but F of Mn. So in other words, you can say that F inverse is nothing but F itself. So these are the kind of answer options that you may have. Okay, take one more. Say F from R, say n to n, Fn equal to n by 2 if n is even, n plus 1 by 2 when n odd. So the question is about 1 1 on 2. Okay, so let us see. Now here F is from n. Okay, so F of 1 is odd, so that is 1 plus 1 by 2, and so it is 1. F of 2 is even, so that is n by 2, so that is 2 by 2, and so it is 1. Now from this we can definitely say that F1 is not equal to F2. Sorry, F1 is equal to F2, but 1 is not equal to 2. What does it mean? Therefore F is not 1 1. What can I say about on 2? It's there. Say F of 3 is odd, 3 plus 1 by 2, and so that is 2. F of 4 is 2, and so on. You will get every natural number as the image, so there is no question of having not on 2. So it is easy to see F is on 2. So it is not 1 1, but it is on 2. Okay. Now if F from A to B and G from B to C are two functions such that GOF from A to C, and that is 1 1, then F from A to B is blank. So that is the, now the options are given, say 1 1 on 2 or kind of things. Okay, so GOF is given to be 1 1 and you want for F, so we definitely prove that F is 1 1. So for that let us take fx1 equal to say fx2, and if we apply g on both sides, so g of fx1 equal to g of fx2. That means GOF at x1 equal to GOF at x2, but GOF is 1 1. GOF is 1 1, and that would imply x1 equal to x2, and so that would imply F is 1 1. Okay. Next, say f from A to B and g from B to C are 1 functions, then GOF from A to C blank, the answer will be again 1 because both f and g are 1 GOF is also 1 you can easily check GOF at x1 equal to GOF at x2. This would imply g of fx1 equal to g of fx2. Now because g is 1 we can apply that, so we are having fx1 equal to fx2, and now again f is 1 so we can have x1 equal to x2, and so this would imply GOF is 1 so that option you have to select. Okay, next let us see if let us have one example where you are having okay, if f from n cross n to n f of mn equal to m plus n, then what can you say about f? Okay, so f of n cross n is equal f of n cross n to n, and the function is f of m comma n equal to m plus n. So that is easy to check that it is not 1 f of 1 plus 2 is 1 plus 2, that is 3. Can you say f of even like this 1 plus 4 equal to 1 plus 4 equal to 5, and f of 2 3, so 2 plus 3 equal to 5, so f of 1 4 is equal to f of 2 3, but 1 4 not equal to 2 3, and therefore f is not 1 okay. What about onto? Only one element you will get, that image is not there, otherwise all the elements will have the images. 2 is there like f of 1 is 2, 3 is there like f of 1 2 is 3, only one element is not there in the image, and that is 1. 1 is not in there in the range of f because there is no mn such that f of m comma n, that is m plus n is equal to 1 okay, because all elements are from natural number. So that means range of f is not n, and therefore f is not onto. Okay, so this function is not 1 that means neither 1 nor onto, neither 1 nor onto. Okay, thank you.